Okay, take a look at page 70, and we're moving on to talking about something called enthalpy. An enthalpy change, which we show our variable as delta H. Remember that delta means change, and the H, the capital H, is enthalpy. Enthalpy change is the amount of energy absorbed or released as heat by a system when the pressure is constant. So basically, if you have heat moving in or out of a system and the pressure of the system stays the same, you can call that heat enthalpy. It's basically a fancy word for a special kind of heat. So you can have an endothermic or exothermic system showing the heat going in for endothermic or the heat going out for exothermic. For instance, an endothermic system, you can start with your reactants at a certain amount of energy. They gain energy to become products. So overall, the products have more energy than the reactants. And this difference in energy is your enthalpy delta H. And for an endothermic system, it's positive because the overall energy is going up. Reactants are less than products. Products have more energy than the reactants. For an endothermic system, that's true, but for an exothermic system, remember the system loses heat. So your reactants start off with a certain amount of heat, and then they lose the heat overall to become products. So this heat change is still called delta H, but now it's going down, so it's negative. And that's because the products are now less energy than the reactants. In an endothermic system, we learned this earlier, energy is absorbed. That means Q will be positive, which again we talked about before, and now we've just now learned that that means delta H is also positive. In an endothermic system, you break bonds overall. Energy appears in the reactant side before the arrow. So there's three different ways you can write the same information. It's sort of like three different synonyms of each other. You can write the reaction, and out to the side you can put that delta H is positive, and that tells you it's endothermic. If it's positive, you could add it to the reactants. So instead of writing the reaction and putting a positive heat to the side, you could put that amount of heat on the reactant side of the reaction. In fact, you could put it as a number, or you could just write the word heat. So you could put it as the word heat, or you could write the number for how much heat. Excuse me. The important thing here is when it's endothermic, heat is part of the reactants. Because for an exothermic system, when the energy is released, that means we've talked before about Q would be negative. We also just learned that the delta H would be negative. So you're forming bonds here, and energy is going to appear on the product side after the arrow. So the three ways you could write this: with an endothermic system, we wrote the reaction, and out to the side we had a positive enthalpy. With an exothermic system, we write the reaction, and out to the side we have a negative enthalpy. When it's negative, you add it to the product side because it's going to leave the system on the product side. But you're still going to add it. So this is the trick. When it's negative and you're writing it in the reaction, you're just saying that the heat is on the product side, but it's a positive amount of heat. It's just the negative tells you to put it on the product side, whereas this positive over here told us to put it on the reactant side. So for enthalpy, positive and negative does tell you if it's going up, being absorbed, or going down, being released. But it also tells you if heat is a reactant or if heat is a product. When you write the heat on the product side, it is still a positive amount of heat. Heat of reaction, or enthalpy of reaction, is the energy involved in a chemical reaction. We measure it in kJ, kilojoules. There's this fancy looking equation, delta H of reaction, so the change in enthalpy for the reaction is equal to, and then there's this thing, which is a capital Greek letter called sigma, and it means the sum. So it says the sum of all the heats for the products minus the sum of all the heats for the reactants. All that really means is you add up all the products, you add up all the reactants, and then you subtract total minus total. Okay, don't overthink it, even though there's this fancy Greek letter. It's not a big deal. It's really simple math, I promise. Don't freak out. Thermochemical equations are chemical equations that include the enthalpy change. So the coefficients represent the number of moles, and delta H of F is called the heat of formation. It tells us how much energy was absorbed or gained to make 1 mole of that compound. For example, liquid water has a heat of formation of negative 286 kilojoules per mole, which means that to make liquid water from hydrogen and oxygen, the elements have to release 286 kilojoules of heat. That's what that heat of formation means. Elements in their natural state, so an element by itself will have a heat of formation of 0 because it doesn't take any energy to be yourself. I'm going to give you a moment to write that. Okay. Let's look at the top of the next page. Here's that formula again. The heat of reaction is the sum of your heat of your products minus the sum of your heat of reactants. And again, the math here is, I promise, not very complicated. Here's what you do. For each reaction, use the heats of formation in the chart. I will always give you a chart. You don't have to memorize it. Use it in the chart to determine the heat for each reaction. Predict whether the reaction is endothermic or exothermic, and if energy is absorbed or released, write the thermochemical equation. Energy values in the equation should always be positive. Remember that exothermic means the energies in the products, endothermic means the energies in the reactants. This seems like a lot of information. We're going to do it, and you're going to be like, oh, this is really easy. So, our formula says we're going to take the products minus the reactants. So what we're going to do is, here's the reaction. We need to do the products, which are zinc and 2HCl. We need to add those up and then subtract the reactants, which are the ZnCl2 and the hydrogen. So we're going to plug in the numbers from the chart to do that. Now we have a little bit of a problem, which is that zinc by itself is not in the chart. But zinc is an element by itself. It'll have a heat of 0. So since it's an element by itself, for the Zn, zinc, we're going to just plug in 0. Then it says 2HCl, so I'm going to add 2 times HCl, and I have to go in this chart, and I have to find the number for HCl, which is negative 167.16. That'll add up my products. Then I have to separately subtract the sum of my reactants. So for ZnCl2, I go to the chart. It says negative 415.1, and then I have to add hydrogen, Hydrogen, H2, also not in the chart, but this is an element by itself. The only element here is H. And when it's an element by itself, its heat will be 0. So for the hydrogen, I'm using 0, and for the zinc, I'm using 0, because those are elements by themselves. So now I can simplify what's in these parentheses. Basically, 0 plus is obviously not going to change anything. So I do 2 times negative 167.16, and that's negative 334.32. Then I'm subtracting, adding the 0 here, again not going to change anything, so this is just negative 415.1. When you type this in your calculator, be careful that you don't miss one of the negatives. If you skip one of the negatives in your calculator, you're not going to get the right answer. Negative 334.32 minus negative 415.1 comes out to 80.78. And we're going to be using units of kilojoules for this. So that was step 1. We just added and subtracted. Step 2 says predict whether it's endothermic or exothermic and if energy is absorbed or released. This was a positive answer that we got here. So when it's positive, we just learned on this page, when it's positive, it's going to be endothermic and energy is absorbed. So for step 2, I say it's positive, so it's endothermic. And I say, since it's endothermic, energy is absorbed. See, easy, not so bad. For number 3, write the thermochemical equation. Energy values in the equation should always be positive. Remember, if it's exothermic, energy is a product. If it's endothermic, energy is a reactant. So, this one was endothermic. Energy should be a reactant. So I'm going to take this amount of energy and I'm going to make it a reactant, 80.78 kilojoules. It's going to be on the reactant side of my arrow with the other reactants, ZnCl2 plus H2, and then the products will be on the product side, Zn plus 2HCl. Really, all you do is you copy this exactly in here. Just copy what they typed for you exactly in here. And then if it was endothermic, you put the heat on the reactant side, added, positive. If it were exothermic, we would put the heat on the product side, added, positive. And I'll do an example of an exothermic with you right now. Calcium carbonate reacts with hydrochloric acid to form calcium chloride, liquid water, and carbon dioxide. So we are supposed to do products minus reactants. So the products here are CaCl2, H2O, CO2, and it's minus the reactants, which were CaCO3 and 2HCl. So if I go plug stuff in for that, the CaCl2 in my chart is negative 877.3. That's got to be plus water, which in my chart is negative 286, which is plus CO2, which in my chart is negative 393.51. I am running out of room. I should have written smaller. And that's minus the reactants, which were CaCO3, which in my chart is negative 1207. And that reactant is plus the other reactant, 2HCl. So it's got to be 2 times the number for HCl on the chart, which is negative 167.16. I'm sorry, I ran out of room. I'm writing all sideways here. Again, since this says 2HCl, you do have to multiply the number from the chart for HCl times 2. So we can simplify everything in these parentheses. The first set, I'm going to add negative 877.3 plus negative 286 plus negative 393.15, or excuse me, 0.51, that's important, Make sure you hit all the negatives in your calculator. Again, if you skip a negative in your calculator, it's going to get you the wrong answer. And then over here, negative 1207 plus 2 times negative 167.16 is negative 1541.32. And then to get my final answer, negative 1556.81 minus negative 1541.32. Overall, that comes out to negative 15.49, and again, our units are going to be kilojoules kJ. So for step 1, every time I add up all the products, I separately add up all the reactants using the chart. And then once I have the total products and the total reactants, I just subtract products minus reactants to get this number. For step 2, we're just saying endo or exo, absorbed or released. We got a negative number here. And when we get a negative number, that means we're looking at an exothermic reaction and energy is released. So for step 2, I can just write exothermic, comma, released. For step 3, we need to write the thermochemical equation, where I write the reaction they gave me, and I have to add the heat into the reaction somewhere. So first, just copy the reaction, like straight down, exactly how they typed it. Just copy exactly what they typed. Then, after you have copied exactly what they typed into this line, you're going to take this number and decide if it goes on the reactant side or on the product side. When it's exothermic, we wrote down it goes on the product side. So I'm going to take that number and I'm going to write it on the product side. And it has to, when you put it in the equation, it has to be positive. So I know it was negative when I calculated it, but that negative just tells me it goes on the product side. When it's on the product side, it's going to be positive. The negative tells me which side it goes on. Okay? Feel free to try number 3 yourself right now. And then you can check your work from the key in my book. But I'm going to go ahead and, yeah, let's turn the page. Page 72. We got to talk about phase changes and heat curves. Change of physical state is also called a phase change. The temperature of a substance is constant, so it does not change during a phase change. While something is melting, it has a constant temperature. While something is freezing, it has a constant temperature. Melting and freezing, water, for instance, will always be 0 degrees the entire time it's melting, the entire time it's freezing. When it's melting, the phase changes from solid to liquid. Molecules speed up, move further apart, and absorb heat energy. That means this is an endothermic change. Freezing, the phase changes from liquid to solid. Molecules slow down, move closer together, and release heat energy. That's exothermic. Vaporization, you go from liquid to gas. The molecules speed up, move further apart, and absorb. Again, absorbing would be endo. Condensation, they go from gas to liquid, so the molecules slow down, move closer together, and release heat. That is exo. Sublimation might be a new one. This is when phase changes from a solid directly to a gas. This happens with like dry ice. Molecules speed up, move further apart, and absorb heat energy. That's endo. And then the opposite of sublimation is deposition. Phase changes from a gas to a solid. The molecules slow down, move closer together, and release energy. That's exothermic. Heating and cooling curves show energy changes. All matter follows the curve when energy is added or lost. Horizontal portions of the curve indicate a physical state change. So the temperature remains constant when it's horizontal, right? If your temperature is on your y-axis, which it is, and there's a flat line, that means the y-coordinates are not changing. There is a change in particle position, resulting in a change in potential energy. They're changing position, that's a change in potential energy. Slope portions show a temperature change, which indicates a change in the thermal energy, or the heat energy, or the enthalpy as well. So we gotta label this heating curve for water, where at part A, and you may remember this from like unit 1, yes, we're doing this again. If this is water, we've got 0 degrees Celsius here and 100 degrees Celsius here. It is, when we go this direction, we've got melting. Or, whoop, nope, sorry, that's wrong. This is the spot where it's solid, and then on this direction, it's melting, and this direction, it's freezing. Here, water is liquid, and if we go this direction, we've got vaporization. And if we go back the other direction, then we've got condensation. And up here, it's a gas. Notice that when it's melting and freezing, it's 0 degrees the whole time. When it's vaporizing and condensing, it's 100 degrees the whole time. So down here, we have the lowest energy. And up here, where it's a gas, we have the highest energy. From here, you can move on to the practice page on page 73, because that's all the notes I have to give you.